um, on my PowerPoint. Oh, it closed. Okay, quickly. Okay, come on. Okay.
All right, I think we're ready to get started.
And we are live. Okay, this is the screen that's sharing.
Mm-hmm.
Okay.
Yep.
While we're waiting here for the stream to start and everyone to join, I'll do a little quick review. So, hi everyone, my name is William, and welcome. And I'm joined by Rachel Bauer, and welcome to the Multiculturalism at the Observatory's first observing night. As I said, my name is William Solorio, and I'll be your guide to the unknown for tonight. We will be going over some basic but important questions about our universe that will reveal how bizarre reality might be. By the end of this night, you might find yourself questioning what gravity and time really are.
But not without appreciating how important these two are for the existence and development of the universe. Science is a collaborative and important process, and to highlight the importance of representation and collaboration, we'll be talking about the contributions of Hispanic physicist Dr. Alejandro Curici. Truly, the universe is a wonderful and mysterious place, and it gets more wonderful and mysterious as we dive into what makes the universe tick. We'll be covering some topics that are thoroughly complicated and take time to digest, so we will periodically stop, ponder, and answer some questions to get our minds going. Whenever we reach a slide that looks like this, please feel free to respond to the question or ask any questions in the chat. As I said before, I'm joined by Rachel, and she will be monitoring the chat. So please don't hesitate to ask questions at any point. So before we truly begin, let me talk a little bit more about myself. So I was born and raised here in Colorado, and both of my parents are from Morelia, Michoacan. I grew up in the city of Northglenn and spent most of my time, most of my childhood, wondering what lies beyond the stars. My parents moved here to the United States a year before I was born, and I haven't gotten the chance to visit my family in Mexico yet. But that hasn't stopped my dad from showing me all the stuff he did growing up in Mexico. Like for example, every year we watch the Toritos de Petate. It's a festival that happens around every Easter, where people create these big costumes and out of a material known as petate. It's really fun to do. Rachel, would you like to say some words?
So hello everyone, my name is Rachel Boyer. I'm from Twin Falls, Idaho, and I'm currently a graduate student here at CU Boulder, and I'm happy to be assisting William tonight.
So the setup for tonight is remote, but we are here at the Sommers-Bausch Observatory at the University of Colorado Boulder. The building was built in 1953 and features two 20-inch telescopes, which are the ones we're going to be observing objects with tonight. And I don't know if you can see, but it's actually behind us. We don't really have a good camera angle, but we also have a 24-inch Bowler and Chivens telescope, which is the one right here in the middle, and a heliostat amongst other instruments. We will be observing the night sky with one of the 20-inch telescopes. And tonight's observing night is part of a program here at the university called Multiculturalism at the Observatory, where we aim to provide outreach or observing nights to highlight the contributions of Latin astronomers in astronomy and astrophysics. We'll be looking at some deep sky objects tonight, and when we do, I'll switch over to the program we use to control the telescope. Now, let's begin into our journey into mystery, perception, and the universe. I want to begin tonight with a quote from a play written by famous author William Shakespeare from the play As You Like It. All the world's a stage, and all the men and women are merely players. They have their exits and their entrances. We know where we live and what a universe is, but why does it exist? And how and why does our universe work in the way that it does? I want all of you to keep this question in mind as we go through tonight. What is the nature of reality? Let's go back to the Shakespeare quote. Well-known physicist Brian Greene put our universe in this lens of a stage play, and I think it's a really good analogy for the universe. So imagine, if you will, that our universe is exactly like a theater stage. The actors are actually the planets, stars, black holes, etc., while the stage itself is space-time, as we'll talk about later on. The big grand play is the story of our universe. We know that the actual stage is made of wood and that it's a flat surface, but now let's put our question that we talked about in the beginning in the context of this analogy. What is that stage that our universe is made out of, and how does it work? What is the nature of the stage? So, we want to understand the universe and all of its intricacies. Let's start with this. The universe is like the stage of a play, and the actors are the planets, but what tells the actors how to act? Why do, in the universe's case, they orbit each other or exist in a stable state? Well, here's where we get to the script for the play. They are the four fundamental forces of the universe. They are like the script that tells the planets how to move and how to behave. Let's begin with the first one, which is the strong force. It's the strongest of them all, and it's the force that keeps the nucleus of an atom together. We are followed by the electromagnetic and electrostatic force. This one's the force of attractions due to charge. Basically, your magnets, your balloons sticking to your hair after you rub them. The force of attraction due to charges. The third one is the weak force, which is responsible for nuclear decay. And while these three forces are super important, they're not as interesting and important as this final one. This one we can feel on a daily basis, and it truly is mostly responsible for the shape and structure of our universe. And if you couldn't guess from the pictures I have up, it's gravity. So I wanted to ask you all, what do you know about gravity? It could be anything. Again, please feel free to type in the chat any questions or responses to the question here. Gravity, where have you heard it from? What do you think it does to shape our universe? And
Yeah, actually, as I'm kind of thinking about this, Liam, I honestly, the first thing that comes to my mind is like those videos on YouTube of people like falling off of things, like those like epic fail videos. Like I feel like that's like the first thing that comes to my mind when I think about gravity.
And like I said before,
it's one of the four fundamental forces of the universe, so we really can't escape gravity, no matter how much we might want to. I know for a lot of us too, the first thing that comes in mind is Isaac Newton sitting under a tree, eating the apple, or not eating the apple, but seeing the apple fall and then thinking, wait, why do things fall? What is falling?
We have one person online who says what they know about gravity is that higher mass objects exert more of a gravitational force.
yes.
Yep, that's Newton's theory of gravitation, right? The more mass something has, the more force of attraction it has. It's directly proportional to the mass. Brilliant. Well, let's move on. Here we go. So yeah, gravity is what's keeping us stuck to the ground, keeping our planet and our solar system in orbit around the sun. And it's super important force that we can detect with our own senses pretty easily. But what really does that mean? Well, while it might be the weakest force, it is the force with the largest range. This force is intrinsically tied to mass and space-time, but we'll cover this shortly. First, let's take a look at what gravity does in our universe. So while other forces have a greater impact on the subatomic world, with the exception of electrostatics, magnetism, gravity has a large role in shaping the universe. There's a lot of things gravity does, but here are the main ones: star formation, planetary formation, planet system formation or solar systems, and planet and star evolution. I put these two pictures here because they sort of represent what I'm talking about. The one on the left is a picture of a protostar inside of a nebula, taken with the ALMA telescope. Both of these pictures were taken using the ALMA telescope. And over here is a protoplanetary disk, which we'll talk about later when we talk about planet formation. Some of the most basic materials that can be found in space are dust and gas. With stars, we can rewind the cosmological clock all the way back into their infancy: gas and dust. Nebulas can be areas where clouds of gas and dust roam, and stars form inside of these clouds. Gravity is what's keeping these clouds together. Otherwise, the gas particles would just fly away from each other and never form into clouds. This is a picture of a giant gas cloud, which again, just got gas particles and dust. In the clouds, the gas particles are constantly moving, while over time, these causes the particles to collide and create dense regions of gas. Gravity then causes these regions to contract and become more dense. Since gravity is the force of attraction due to mass, a star is therefore born after enough pressure builds high enough in the center that it actually starts what's known as nuclear fusion. And this leads to stars. So here's a picture of our sun taken using the atmospheric imaging assembly of NASA's Solar Dynamics Observatory. A star then lives its life in a constant balance between outward pressure from all the heat, of course, because all that fusion is happening in the core, and the inward force of gravity. The star will eventually run out of fuel, which are the materials it needs to continue fusion. What happens when this balance is broken? One such fate of when the balance is broken is what's called a white dwarf. This is an image of Sirius A and Sirius B. Sirius A is a large star and B is its companion white dwarf star. It was taken using Hubble's the telescope. And I don't know, it's kind of interesting that you can see all the mass of the star is condensed into this small, tiny volume that is the white dwarf. Anyways, to see what happens, let's now switch over to the telescope. Here we are. So this program actually controls the telescope. And there's a lot of information with this interface, but basically here we can see the night sky. This orange outline boundary here is actually what the telescope maps as the roof. So anything inside of this boundary are objects we can see with the telescope. If we move over here to the find, we can search for objects, and we're going to start with not necessarily a white dwarf, but I'll explain a little bit. But we'll start with the Cat's Eye Nebula. Here we click center to make sure the telescope wants to look at this object, and then we're going to slew to move the telescope into position. But first we need to click find, center, and then slew. Look at it go. Fantastic. Now that we're centered on the Cat's Eye Nebula, we're going to switch over to camera. using the CCD. We're using the filter to look through it. It's called the R filter. And here, now that the telescope is pointing at the object, we're going to change a couple settings. So the time, exposure time, we're going to change to 30 seconds because the object is relatively far away from us. So we want to expose it long enough for it to gather enough light so we can see the object. The binning will be 2 by 2 to make sure we have the right dimensions for the picture. The frame, light, no reduction, and it looks like we're ready to take our picture, except that was on the focusing tool. So let me change this here, 30, 2 by 2 light, and we're ready to take the photo. And to make sure that the photo is automatically saved, we do have to do some settings in the folder over here. To making sure we're storing the images. Now that we have the location we want to save the photos ready, we will receive an error. There we go. Here's the filter wheel, by the way, that we used to change the filter. So while that's taking the picture, let's pick up where we left off. So remember, the balance between pressure and gravity is now broken, and the star begins to die. It will enter a red giant stage where fusion stops and the core contracts, but the outer shell of gas expands. After this, all stars reach this stage, by the way. If stars don't have enough mass to reach the supernova status, they instead eject their outer layers of gas until nothing is left but their cores. The cores are what we call the white dwarfs, and the outer layers of gas actually begin to glow because the white dwarfs, the cores, emit radiation. This can create beautiful patterns because, again, the dust and gas is now illuminated by the radiation into nebula. And here is the picture for one such nebula. So if we go here, we can actually change the settings around a bit. But here's the Cat's Eye Nebula. And again, this is just changing the contrast. There we go, to see the image a little bit better. But Cad Sign Nebula, this is one of the planetary nebula I was talking about with the white dwarf here in the center. And this weird gas area around it, those are actually the rings of the gas layers that were ejected as the star was dying. The new gas interacts with the old ones as it keeps ejecting out layers of gas, which creates cool shapes. Again, I don't know if you can see it very well, but it creates really, really beautiful rings. The Cat's Eye Nebula is about 3,000 light years away from Earth. Light year is the distance it takes light to travel in a year. So it's really far away. And it's in the constellation of Virgo. A little bit of a fun fact, each little ring has enough mass to equal all of the mass of our planets here in our solar system combined. Again, remember, this is a star we're talking about. X star, now it's just a white dwarf. The remains of the dust, gas, and elements can form into new stars, planets, and etc. So it's exactly similar to how the star formed in the first place in a nebula. Now new stuff can form in this dying star.
So something that really fascinates me about these like planetary nebula is how like big they appear on the sky. Because if we kind of look at this picture, we can kind of see these other points of light that are also in the frame, and those are also other stars, right? And we're not, I guess we don't know necessarily how far away they are, but like if you think about it, like this whole nebula used to be just like one of those little points, and through the process of dying and expanding, like it's shot off gas like a really far distance. I think that's so cool how this little tiny little pixel has basically turned into this giant cloud. I think that's awesome.
I couldn't agree more. And a little bit of a fun fact for you all. Each little ring is actually created every 1.5 thousand years or so. And this isn't the only pattern that can happen. There's way other cooler patterns that can occur from planetary nebula. I'll highly recommend you all check it out. Well, let's go back to the slides here. We're just going to stop here momentarily to see if you have any questions about the object you just observed. But as you're all thinking of questions or typing them in the chat, I do want to show you what the nebula looks like taken by the Hubble telescope. So Hubble is in space, and it's got very, very intricate technologies, so it can take really, really cool pictures. But here are the rings I was talking about for the planetary nebula. This is actually kind of like a cut view. So if you were to take an onion and cut it in half, you could see all the rings. The same concept here. We're like cutting through and seeing all the rings from our perspective. It just so happens that we have that perspective here on Earth.
And in case you're wondering, in case the audience is wondering why like our image is kind of black and white and the Hubble image is color, it's basically because you can kind of think of like our telescope as like a bucket that's like, or collecting rain, like if you're trying to measure how much it would rain one night. So it's this big bucket, and you set it out there, and it's collecting drops as they come in. And our telescope kind of works the same way, like it's just counting the particles of light as they come in, and it's not necessarily assigning them a certain color. We could totally make a colored image if we kind of like took a few hours and used different filters and kind of combined them. There's like a little bit of artistry kind of required to make color images, but in case you're wondering, like kind of the live viewing, we'll only get kind of black and white images, whereas like if you had a lot of time and a beautiful telescope like Hubble, you could make these really awesome, beautiful, stunning color images.
And that's also why we have to change the exposure time for different objects as we see them. We don't want to collect too much light to where the image becomes overexposed.
We have a question on the chat, and it says, what determines kind of like the shape and geometry of these rings in the nebula?
Right. So
gravity, the focus of the talk tonight, a lot of it is shaped by gravity. So I said earlier, gravity has a large range. So nearby stars or other massive objects can have an impact on how the rings form. And again, a lot of it does have to do with the star itself, how large it was and how much of an effect its original gravitational field had, and how much it has after it's becoming a white dwarf. So again, it all comes down to gravity. That determines the shape of the planetary nebula.
Yeah, I totally agree. Like a lot of the times we'll see these kind of like concentric spherical shapes because gravity kind of acts like kind of radially inward and kind of in all directions. And if you kind of think about it, like as the star was dying, it was just blowing off its upper layers and atmosphere. So you can think about it almost just like puffing up like a bubble. And we're kind of seeing, this like kind of 2D projection of these big bubbles, like if you were actually to be in the nebula.
Magnificent. Let's us continue. So, white dwarfs and planetary nebula are one possible fate for a star. The other one is more explosive in its conclusion. These are called supernovas. If the star is at least 8 times heavier than our sun, an event known as a supernova will occur. So again, rewind back to the point where the star starts to die. The nuclear fuel of the star is all used up, which causes the core to cool down and the outward pressure to decrease in the core. So gravity then takes over, since it's the only force now acting on the core, and the star collapses so quick, in seconds actually, that it causes an explosion, supernova. Some quick fun facts about supernova as you observe this glorious visual here. A supernova occurs somewhere in the universe every 10 seconds, and supernovae are the sources of our new elements, radiation, and neutrinos. So they're like cosmic particle accelerators. From there, after the supernova, it pretty much depends on how much matter and therefore mass the remaining core has. If it's heavy enough, gravity will be so strong that it collapses again and forms a black hole. Or if it's not large enough to become a black hole, but still heavy enough to exist, it just really stays as a dense core that's called a neutron star. So we've got stars down. Now let's move on to the main actors of this universal play. One important question astronomy has been trying to answer for a while is how planets and planetary systems form. And a lot of the theories are based on this really, really basic theory or hypothesis that's known as the Cant-Laplace nebular hypothesis. And it goes a little something like this. If the universe at its most basic is just gas and dust, then solar systems form as a result of gravity pulling the particles in the cloud together. So planets formed from the dust and gas clouds, just like stars. And what a better way to learn more about planets than by looking at one with our telescope. So let's switch over to our telescope view. What's a good planet to view tonight? Let's see here. Again, we're going to find and searching for our object. Let's look at Jupiter. Spelled wrong. There we go, Jupiter. So we click find, we center it to make sure the camera knows what we want to look at, and slew to change the telescope's position to point at Jupiter. There it goes. We've arrived. So going back to the camera settings, this time instead of 30 seconds for our exposure, Jupiter is way closer to us and we don't want to overexpose the image. So we're going to go for something lower. Let's do 0.3 seconds for exposure time. There we go. Same binning frame, and we'll take the picture. So here's the picture we took. I changed the method to heuristic, and even so, the image looks really, really bright. So this means we overexposed the picture, so we need to have an even lower exposure time. So instead of 0.3 seconds, now let's try 0.03 seconds. This is looking better already. Even still, it looks like the image is overexposed. Jupiter is way closer to us, so we need to have really low exposure time. 0 seconds. Let's try 0 seconds and 1 by 1 bitting. Oof. If I mess with these settings here a little bit, you can actually see some of Jupiter's Galilean moons. Very, very bright. Let's try a different filter. Oh, true. So we're moving the filter. If you were here, you could hear the camera switching filter, tracking. It's ready now. So let's go to the camera. Ready. Spinning. Take photo. That turned out really nice. Again, here you can barely see some of the Galilean moons. But Jupiter, as I was talking about earlier, over time, so usually around every young star, there is what's called a protoplanetary disk. And basically what that is the same thing as we were talking about before, just a ring or a disk of gas and dust, and with a star in the center. And this is where the planets and other objects can form. With planets, the dust particles accumulate in the inner hot parts of the disk, where they collide with one another, and through gravity, they begin to stick to one another and build into rocky formations or rocky planets. That's not what happened with Jupiter, though. The story is a little bit different. Here, the dust particles in the cooler parts of the disk accumulate again through gravity, but they grow fast enough that they start to trap gas as it's forming. This means it's not a rocky mass or a rocky planet, but it becomes a gas giant instead. Hence, Jupiter. This image doesn't really do Jupiter much justice in terms of just how big it is. I mean, if we were to go from one end to the other, it'd take 11 Earths lined up. And to equal the mass of one Jupiter, we'd need about 317 Earths. The gravity on Jupiter is 2.4 times that of the gravity of the surface of the Earth. So if you were to weigh 100 pounds here, you'd weigh 240 on Jupiter. That's not all for Jupiter's gravity, though. Its gravitational field is so strong that the planets, especially Earth, could not have formed the way that they did if it wasn't for Jupiter.
Yeah, and I think this image is so beautiful because you can actually see like the different layers on Jupiter, like the different cloud layers. And if you ever have a chance to come to the observatory in person, we have some open nights available in person. You can look through the telescope and actually see the different colors of the bands of Jupiter, and it looks just beautiful.
Some interesting facts. These bands are actually clouds. Like I said earlier, Jupiter was a gas giant, is a gas giant. So a lot of the surface is just gas, clouds, storms. That's what the big red spot is, of ammonia and water. What a lovely planet. Let's now switch back.
Actually,
Before we go, let's see here. No. A little bit. Maybe if I swapped it to. No. Here we go.
So yeah, we just changed the kind of the contrast on the image a little bit here. And the reason why we did that is Jupiter looks a little bit worse, but we can actually see kind of these 4 points of light. There's 3 over on this side, and then there's 1 over on this side. And those are actually moons of Jupiter. Jupiter has like just a ton of moons. I think it's like 80 or something. Like it's just so many. But it has kind of these like 4 really large bright moons. And our telescope is actually picking them up. And these 4 moons were actually first discovered by Galileo himself when he kind of looked through a telescope for the first time in Jupiter and saw these points of light. And maybe he would have thought at first that they were stars in the background, but as he continued to observe Jupiter, he noticed that they would just kind of move around and stick around the planet. So he figured out they must be moons.
The moons are really cool too. One of them is Europa.
I think, and that's the one where it's. Correct me if I'm wrong, but that's the one that has water, where the surface is up, but it's got liquid water the further you go towards the core.
Yeah, Europa is just a fascinating moon because we think that it has an ocean, like William said, and then that oceans kind of lead us to go, okay, maybe there's life there.
Yeah.
And so it's a huge focus for upcoming missions to actually go there and check it out and see what's happening over there.
Alrighty, let's go back to the slides. Object Jupiter. And if you guys have any questions, please feel free to type. And while you type or while you think of anything, I wanted to show you the picture of Jupiter, but instead taken with Hubble. Again, here's Hubble, but you can really see the different clouds and storms in great detail. This is actually a recent image. It was taken in 2019, so recent relatively, but yeah, it looks amazing. In case you were wondering, Jupiter is a good, let's see here, 376.16 million miles from Earth. So it's not the 3,000 light years that the planetary nebula was, but it's still pretty far away. A little bit of a spoiler here now that we have the slide, but we previously reviewed how gravity is not only responsible for the formation of stars, but for their whole life cycle as well. One of the many fates of stars is the very famous and interesting phenomenon of black holes, regions of space where gravity is so strong that not even light can escape. This isn't the only way black holes form from a star collapsing, of course. Many galaxies actually have supermassive black holes in their center. Our galaxy, the Milky Way, has one, and so does our neighboring galaxy, Andromeda. Let's take a look with our telescope. Oop. So here we use the O3 filter to look at a planet, but since we're going to look at a super far deep sky object now, let's switch back to the R filter. There we go. All right. Now, we want to look at Andromeda, our neighboring galaxy. Alrighty, there it is. Centering it, and now making sure no one's in the way, we're going to move the telescope to point at Andromeda. As we can see here, it's barely. Um, hopefully. So here's the boundary, and Andromeda is right there. So it might be well, we'll see, we'll see. So Andromeda is super far, so we actually want a longer exposure time. Let's go for 2 minutes. Um, binning, try 2 by 2. Light frame. Again, we're using the R filter instead of the O3. And let's take the picture. Well, while we wait, let's have a little chat. Continue our chat about black holes and galaxies. So things get very surreal with black holes. Like I said before, the gravity is so intense that not even light can escape. But the boundary of the object, of the black hole, is what many call the event horizon. And it's known as the point of no return for a very good reason. If you were to cross this point of no return, time would slow down to a stop. Oh, and fun fact, if you were to cross this point of no return, uh, I believe your feet would be under a greater gravitational pull than your head. So you would literally be stretched out until you're nothing but a thin uh, string of atoms, which is known as spaghettification. So you're not turned into spaghetti, but it's close enough. One minute left.
I'm curious to see.
If yeah,
Our telescope is kind of like halfway pointed at the wall, halfway pointed at the sky. It's kind of this one thing that we have to account for as astronomers as we're taking our images is that the you know sky appears to be moving around. Of course, we are turning around here on Earth, but as you're looking at things, they might move.
15 seconds left. Whoa.
Looks like we got it.
So it looks like we did successfully take a picture of Andromeda. Let's, editing the contrast here. We can, yep, there we go. Here we are, Andromeda, our cosmic neighbor. This galaxy is 2.5 million light years away from Earth. A light year, again, is the distance light takes. It takes light to travel in a year. So if you're traveling at light speed, the universal speed limit, it takes you 2.5 million years to get here. That's not all. The diameter of the galaxy is 260,000 light years, and it's home to over 1 trillion stars. So you might think our Milky Way galaxy is pretty big, but Andromeda has almost twice the mass of our galaxy, and its supermassive black hole is 80 to 100 million solar masses. While our own Milky Way galaxy's largest black hole only has a solar mass of 4 million, 4 million solar masses. And again, solar masses are just exactly what they sound like, with one being equal to the mass of our own sun. Black holes aren't the only consequence of gravity for galaxies. So because of all that mass I mentioned in Andromeda, and in most galaxies in general, their net gravitational field can reach out into other neighboring galaxies, which is exactly what's happening with Andromeda and our own Milky Way galaxy. What does that mean? Well, in approximately 4 billion years, the gravitational pull will cause Andromeda and the Milky Way galaxies to collide. Well, that's a little hyperbolic. It's more like they'll merge, but it'll happen in about 4 billion years, more or less.
Yeah, one of the things that I think is so interesting about like the Milky Way and Andromeda merger is like it seems like very apocalyptic, right? Because Andromeda is actually bigger than us, like you said. So it seems like they're gonna come and just like eat like our own galaxy, and like what does that mean for like our solar system and whatnot. And there's like a few reasons not to be worried. Like the first one is that like our sun is actually going to become a giant and swallow the Earth before then.
Yeah.
So that'll take care of us. But yeah, like you said, it's like more like a merger, because even though there's so many stars with these galaxies, the likelihood of two stars actually smacking into each other is so low because space is just so immense and things are so far apart. So we would definitely, change our arrangement of where we are in our own galaxy as we become a new galaxy, but our star isn't necessarily going to like collide into something else. Like it'll just kind of be a part of a new arrangement of stars and a new type of galaxy.
That's definitely something to wait for. Whew. Remember, if any questions, feel free to type them in the chat. So let's switch back here to our little slides. So we'll pause for a little bit. If you have any questions or any burning quandaries you'd like answered, feel free to type in the chat. But as you do that, I want to, as we've been showing previously for the other two objects, show you a picture of the Andromeda Galaxy. But this actually wasn't taken using Hubble. The one by Hubble is actually too big and it's like cropped to view. But this was one taken by an astrophotographer using a TMB 92 refractor telescope. It's pretty neat. And the brightest point here in the center is what we saw when we took a picture of it with our 20-inch telescope.
Yeah, and one of the really cool things about this picture too is you can actually see over here in the corner like another mini galaxy that is a lot smaller than the Andromeda Galaxy. So it's kind of, it's like a little kid or like a puppy, like hangs around the Andromeda Galaxy and is kind of like entrapped like in the Andromeda Galaxy's gravity. So we have a question from the chat. So the question is about how Andromeda and the Milky Way are going to merge. But are they actually going to merge? Or, if they're moving so fast and they have so much inertia, like, wouldn't they just go past each other? Or what's going to kind of make them merge together like we expect?
So one
thing that I haven't mentioned, but it's kind of important to this whole topic of gravity, and I kind of spoiled myself there, but dark matter. So a lot of the mass that we can't see, but we know is there because it's got to be there to keep the structure of the galaxy together, is dark matter. So because of this, the gravitational pull is going to be really intense. Just like you mentioned, the inertia of like a lot of solar systems and planets and stars is of course existing super greatly. And as we mentioned earlier, there's enough distance that we'll feel each other's gravitational effects, but they won't actually collide. So ideally, because of all the dark matter and consequently because of all the gravitational effects that has, they are going to merge, but the inertia explanation does also contribute to why nothing collides or nothing like becomes a new system directly. What were you thinking, Rachel?
Yeah, I would just add to that like, yeah, I agree. Like one thing we haven't talked about is the dark matter component. And dark matter is huge. Like it makes up like upwards of 80% of the mass of galaxies. And when they kind of are gonna come and like merge together, it's not gonna be just like a clean, like just two blobs like become one blob. There's some really fascinating simulations you can find on YouTube of the two galaxies merging. And there is kind of a lot of like slingshotting that happens. So they're kind of approach each other almost directly, and then they're kind of gonna like do this like almost slingshot effect where they kind of dance around each other a little bit before they can become one blob, and there will be like arms of stars that just get like flung off into space, like from all this inertia that's coming into the merger. So I guess depending on, you know, where a star is located on the two galaxies, it could just be like totally flung out into space and not even be a part of the new merger because of all the rotational and like just kind of fast motion that the galaxies are coming in with. But the majority of the stars are going to kind of be captured into this new galaxy. And because we're going to have so much gas and dust coming together, like we kind of mentioned at the beginning of the talk, like it's actually going to trigger like a whole new era of star formation in this new combo galaxy. So it's going to be not only will there be the stars that already existed in the galaxy, but there'll also be like a brand new crop of stars from all this gas coming together.
The slingshotting effect is also something we can use currently. Earlier, I showed a picture of Jupiter, and what we can do is, because its gravitational field is so strong, is when we send probes, we can actually use Jupiter to slingshot them. I don't know if anyone's seen the movie The Martian, but same concept, but in that movie, we use the Earth to slingshot the space shuttle right back to Mars. Anyway, enough pop culture. Let's continue our journey. So remember our initial question, what is the nature of reality? Well, it really does seem that reality starts to break down in black holes. Time slows down to a halt. Gravity is so strong that not even light can escape. What in turn can we learn from this? Let's continue our journey into the force of gravity. Did I close anything? Okay, we're good. Earlier, we shared our thoughts about what gravity is, and I want to return to this question. We've been talking about gravity as a force, and that's certainly how Isaac Newton thought of gravity as. I know someone mentioned in the chat how gravity was the force of attraction due to mass, and the Newton's law of gravitation does state that this attraction is directly proportional, meaning the larger the mass, the larger the force. And the force is also inversely proportional to the distance between two objects squared. So if the distance doubles, then the force is 1/4 of its original strength. This is a really good understanding of gravity that can explain most motion in the universe, but it doesn't explain Mercury's orbit very well. And that's a problem that physicists were very well aware of past Isaac Newton's shining in his fame. So if the planets are actors and gravity is like the main script that tells them what to say or how to move in space, then Newton's theory of gravity is an incomplete script. And it does, because it doesn't explain all the movement, right? This is where physicist Albert Einstein comes in with a different, more updated script for gravity that actually does explain Mercury's precession. Dr. Alejandro Corici has made it one of his life studies to help with this quest to find a complete theory of gravity. And to get to his point and to his research, we first need to go through Einstein's theories of relativity super briefly. Yes, let's start with the very classic twin paradox thought experiment. Thought experiment. So there's two twin sisters, Gaia and Star. And Star wants to take a trip to a star, or let's say a planet that's 6 light years away. She gets on her rocket ship and she travels to the star, let's say at a good 0.6 times the speed of light. So we're not at light speed, we're like a little bit more than half of light speed. So she goes there and then she travels back the same speed. But when she gets off her ship and reunites with her sister, she realized something's off. For Gaia, who stayed on Earth, 20 years have passed. But for Star, her clock reads only 16 years, meaning that Gaia is now 14 years older than her identical twin sister. How can this be if they were both born at the same time? Well, friends, I first want to point out two key features to this problem: time dilation and length contraction. So, special relativity concludes that because light travels at a constant speed, no matter what reference frame, the length of the object and the time it takes to travel change as they approach the speed of light. As an outside observer, we see that the rocket contracts and shortens in length as it approaches the speed of light. And in order for the speed of light to remain constant, as I said, this also means that the time that the rocket travels in changes. It increases. So its length contracts and its time seems to run slower. It increases from our perspective here on Earth, staying. But from stars' perspective on the rocket ship, time seems to be going normally, right? But the other effect does kick in, which is length contraction. You see, from her perspective, the distance to the planet appears to contract. Instead of being 6 light years away, it's actually 4.8 light years away from her point of view. These two effects have to happen in order to make the law work, in order for light to be the fastest and constant no matter what observer you are. We've tested this many times and found that time dilation and length contraction are really important effects if you want precision. So we use it a lot for satellites, GPS, stuff like that. This phenomenon is explained in Einstein's theory of relativity, special relativity. What does this tell us about our universe, though, and the nature of reality? Let's pay attention to time dilation. You see, because time ticks differently depending on if you're the one traveling close to the speed of light, or if you're on Earth, like Gaia, just remaining at rest. This means that time ticks differently depending on your frame, right? There is no universal passing of time. Everyone has their own clocks that tick at their own times, which can be ticking faster or slower depending on your speed and your reference frame. Of course, these effects are not noticeable in our daily lives. We're not traveling at half the speed of light constantly, but they do matter when you need precision or when you do reach those speeds. Yes. So technically, if you wanted to, you could time travel into the future by moving really fast, a fraction of the speed of light. So remember, if you travel at this rate, from everyone else's point of view, your clock will tick slower. So by the time you're done running near the speed of light, you would have actually aged slower and everyone else would have aged faster. Ergo, you time traveled. There is another way to do this. Let's go back to the twin paradox thought experiment and change it a little bit so that the planet that star traveled to is actually significantly heavier and bigger than Earth. What does that mean, you may be asking? Well, that means she not only also traveled to the future because of how fast she was going near the speed of light, but also because of the gravity of the planet. This takes us to Einstein's other theory of relativity, general relativity. And it goes a little something like this. So I have a confession to make. I've been talking about gravity all night as a force, but under Einstein's theory of general relativity, that's actually not the case. It's not a force. Gravity, under Einstein, is a consequence of the curving of space-time. Let me explain. Here's the classic space-time, diagram, and then to explain this, I first need to talk a little bit about space-time. I've been blabbering all about space-time, but not really what it is. So it's kind of what it sounds like. It's space and time. I mean, we're used to moving in three-dimensional space, right? We move up and down, left and right, forward and back. But since we're in space-time, which combines 3D and the dimension of time, that means we can also move through the fourth dimension of time, just as if we were moving in the other 3 dimensions physically. Of course, with time, though, we can only move in one direction, which is forward. I mean, in special relativity, you could, if you were to travel faster than the speed of light, go back in time. But again, speed of light is the limit. We don't really know how to do that, or if that's even possible. So you can't time travel into the past. Sorry. Okay, so now think of this space-time, this fourth dimensional thing, as the fabric of our reality. It's the wooden stage of our cosmic play. The thing is, the stage is not a solid flat like an actual wind stage. Instead, it's more of like a large fabric suspended by the corners, like in this picture here. When we place an object like this paperweight into the fabric, the object sinks and creates a dimple around itself. There's the dimple. The larger the mass of the paperweight or whatever object, the larger the dimple is going to be. These dimples are gravitational fields, and objects experience the fields as they move through space-time. You see, as this ant moves, it's affected by this dimple sort of pointing towards the paperweight, and then it's pointing out of it as it moves through space-time. On a technical level, the curvature, the bending, these dimples reach out to the objects kind of like through a field-like interaction. And for those of you that are familiar with electromagnetism, it's kind of like electric and magnetic fields. But enough about that. So what does this all mean? Well, gravity is therefore the result of the curving, the bending of space-time. It's geometric, but that's not even the full picture of it. It gets even weirder. Remember how I talked about time traveling into the future through gravity? Well, this is another interesting consequence of general relativity. And that's something that we call gravitational time dilation. With special relativity, your clock seems to tick slower the closer you approach the speed of light from the point of view of an outsider observer, right? We talked about this with Gaia and star. But in general relativity, something similar happens with gravity. Gravity is the bending, the curvature of space-time. It's the dipoles we talked about, the dimples, sorry. And the more significant the bend, the greater the dimple is going to be. Physicist Carlo Rovelli once said that mass slows down time around itself. So technically, if you were to live like, and this scenario, of course, ignores the effects of like being farther away from the Earth and maybe traveling faster. But the basic general idea is if you were to live closer to the Earth, you would be under a greater gravitational pull, meaning your time would click slower compared to someone that's living at a higher elevation. Or let's put this in the perspective of the twin paradox. If you were to live on Earth, your time would run faster than if you were to live on planet X, which has a larger mass. Why? Because the one with the larger mass is going to affect time more. Remember the thing about the black holes? How the gravitational pull is so strong that even light can escape it? Well, the connection with gravity and time is why time comes to a halt once you pass the event horizon. It's because of how strong gravity is. All of what we've been talking about tonight has been research that Dr. Alejandro Corici has spent a good 20 years of his life studying. Dr. Corici is a theoretical physicist currently affiliated with the UNAM. It's the National Autonomous University of Mexico. And it's the campus of Morelia. Dr. Corici received his bachelor's in physics at UNAM, writing his thesis on geometrodynamics. Like I said, it's the relativity and the gravity we've been talking about. He then finished his education with a doctorate degree in physics from the University of Pennsylvania in 1997. Just a little bit of context here. Here is Morelia, Michoacan. It's actually right next to Mexico City, but this is where his campus, where he works at, is located. Dr. Corici has worked as an investigator for the Institute of Nuclear Sciences at UNAM. He's also a part of the quantum gravity group as an investigator in the campus of UNAM, Morelia campus of UNAM, where he's been working since 2005. In case you were curious, this is what the campus looks like. Dr. Corici's largest contribution to physics has been through his main research interest, classical and quantum gravitational physics. Everything we've been gone through tonight regarding gravity is something that he's been studying for over 20 years. There's something I haven't mentioned though yet, and it's really important for his research, and that's our incomplete view of gravity. You see, there's a problem. General relativity and quantum mechanics don't really work together very well. With general relativity, I mean, it explains how gravity works on a cosmic scale, but we don't really have a theory that combines the two and explains how gravity also works on the quantum scale. I'm talking the smallest scale possible. It appears as if they're incompatible, but that doesn't mean we don't have theories that try to combine them. And this is what people mean by quantum gravity, a theory that combines these two. One of Dr. Kurichi's research interests lies in solving this issue of incompatibility, and one solution that he's been working with is something that's known as loop quantum gravity. It sounds really cool, and it's even trippier than what it sounds. So loop quantum gravity attempts to combine those two theories by focusing on the background that is space-time. So for a while, we humans thought matter, stuff that everything's made out of, we thought that that was continuous, that it was smooth, not really made up of small little bits. But modern chemistry does tell us that matter is actually made up of individual pieces or atoms. If we take the same approach to space-time, we get loop quantum gravity. In other words, loop quantum gravity, in loop quantum gravity, space-time itself is a fabric woven from fibers. In other words, space-time is made up of discrete little components, just like how matter is made up of atoms. The loops come from a mathematical tool, which we know as connections. And we're going to represent the loop with this raft that's been sitting here ominously for the past 30 seconds. But basically, the loops tell us how a vector changes as it moves in space. And the connections look like loops. That's why they're called loops. Since the loops can tell us everything we need to know about space-time, we can create any geometry that is 3D using the loops. What does that mean? Well, let's think of them as rafts, right? A loop sitting there, a loop, when I say loop, I mean raft. Let's think of a raft just sitting there in the middle of the ocean. It represents a tiny volume of space compared to the entire ocean. And the volume is discrete. It's an individual and separate number that we know. As we add more rafts and people, we can start to make connections between the rafts using planks, wooden planks. And eventually, we can build up into a large network of rafts and planks that sort of resembles a shape when you look at it from this angle. But the loops are the rafts, and the connections are the networks that can be made using the loops. This is similar to how when you have more atoms, you can start to make molecules, and then that eventually builds up to matter. Where loop is sort of analogous to an atom. Something interesting is at this small level of loops, time really isn't there. It's not present. I mentioned we can make any 3D shape out of these loops, but I omitted the fourth dimension of time. That's because as we add more loops, that's the wrong direction. As we add more loops and more connections and the system becomes more complicated, time just sort of seems to emerge. And it's an area of what Dr. Kurichi is trying to study to understand more of how this would work logistically. But each loop does sort of act as its own like circuit of gravitational field. So we start with gravity with the loop on the smallest level. In other words, we kind of solve that issue of general relativity and quantum mechanics not mixing together. Dr. Kurichi has done research on theorizing the ways in which these loops can combine to create the fabric of spacetime. And his work is essential in the quest for completing the theory of gravity, or quantum gravity, and in turn, finding a theory for everything. Dr. Kurichi has also done research on how loop quantum gravity applies to cosmology. This is known as loop quantum cosmology, and it's actually really cool because under this field of research, it actually predicts the Big Bang to not be the beginning of the universe, but more of like a point known as the Big Bounce, where before that, something that's known as the Big Crunch happens. And this picture kind of represents it well. So under loop quantum cosmology, it predicts that there was a point before the universe where everything was contracting, known as the big crunch. Then we have the singularity, the Big Bang, and then it springs up and everything's expanding, and the universe is now expanding at an accelerating rate. That's where we are right now. Dr. Corici is doing research on, again, how to make all of this work logistically. So this is kind of a cool picture, because if loop quantum gravity is correct, this means that space-time is actually made up of like small discrete components. This picture kind of represents that in like an artistic way. So it's like space-time where everything exists and we move in. If we were to break it down to its most basic components, is like these small little crystals. It's kind of like a fun way to picture what everything looks like. So I just went through a lot. I'm going to pause here for a little bit. If anyone has any questions, please feel free to ask them in the chat.
Yeah, I think like this research is so fascinating because I guess the idea is that we want like a kind of like a theory of everything in physics, right? We want like equations that we know will work in all situations and for all types of matter or whatever it may be. And it's so cool to think about like all these amazing theories that people have for what space-time is made out of, like how did quantum gravity exist, and like and to think about the cool things like the beginning of the universe, you know, what was happening then? Was there something before the beginning of the universe? I think, yeah, this realm of astronomy and astrophysics is really incredible.
I couldn't agree more. It's really like important in us figuring out our place in the universe and kind of putting meaning to it a little bit. I'd like to think, but very, very, very interesting stuff. Get a drink of water here. Here it is.
Yeah, I think another cool thing about this is that like gravity is something that we've been studying for so long in physics and astronomy, and we know a lot about it to like a certain degree, right? Like we can make these amazing calculations for sending spacecraft, you know, to other parts in our solar system and whatnot. But like fundamentally, we still have so many questions about like what actually is it? Like we're pretty good at measuring like its effects, but like trying to figure out what it is like is still kind of an active area of research. And then we got a question from the chat. So according to this quantum loop cosmology, was the universe before the Big Bang like our universe, or is it like, does it work differently somehow?
That's a really good question.
While I'll try to answer this to the best of my ability, but the thing about the big bounce and before that the big crunch, it sort of appears like it might be cyclical, right? Like we might be in like a constant loop where it expands, then it contracts, and then there's a big bounce, and that might sort of seem to imply that the universe might have been under like the same rules, the same the same physical rules as our current universes. And if we take the loop quantum cosmology and loop quantum gravity to be true, then we'd sort of assume that it did act or behave like our current universe, that space-time was composed of those small little loop discrete parts. Yeah. Rachel, did you have anything to add on to this?
Yeah, no, I think I agree with you. Again, I'm definitely not an expert in this field, so I don't want to pretend like I am. But like, yeah, I think I don't think we would necessarily expect like a clone of our universe as it is now. I think we would expect, yeah, for the same physical rules to apply. So perhaps it would have formed in a very similar way than to what we see today. But yeah, I think that's a fascinating question. Like, does it change a lot every time there's a big bounce, or like what happens? Yeah, interesting.
And these questions are super important stuff that physicists like Dr. Kurichi are conducting research in. Another question.
So we've got another question here. Is there any evidence in cosmology that might give us some kind of indication of whether this big crunch, so something like the big crunch, would actually happen?
I'll direct that question to you, Rachel.
Yeah. That's a good question. So I think the big crunch is kind of like, it's kind of one of those scenarios that like mathematically and kind of like physics wise like could happen. But at least but when we look out and like gather evidence, like when we observe objects with telescopes and see how fast they're moving and see kind of like their composition, right now the clues are leading us kind of away from that happening to our universe. But I mean, who knows what will happen? So at the moment, it does not seem like the most likely theory. It doesn't seem like we're going to have a big crunch. But if we, continue to research and do more, find more evidence, like, perhaps there's going to be more evidence supporting the quantum loop theory, then that could potentially change. But I think at the moment, it is definitely not the most likely kind of outcome for our universe as it stands.
Right, because
we know our universe is expanding at an accelerating rate, and that's kind of the opposite of the big crunch, right? And as far as evidence goes, it's a little bit difficult to find that, because again, that's like before the Big Bang, right before the singularity. With the Big Bang, it's kind of easier to find evidence for that because we have the cosmic background radiation that we can trace back to the singularity. But just in cosmology, at least, it's way much more difficult to find like direct evidence for the big crunch. But for quantum loop gravity, current evidence that this supported, I know it predicts, I think it's Hawking radiation accurately. I might be wrong on that, but it definitely has its uses there with Hawking radiation. Loop quantum gravity does. Well, thank you everyone for coming. This brings us to the final stages of tonight. Let's finish just by returning to the stage analogy from the beginning. We've learned that the stage of the universe is not a flat wooden structure, but a wooden fabric that warps and dents as things move through it. We have learned that the actors of the play are guided by a script, which are the fundamental forces of the universe. And a big part of the script that concerns the actors is gravity. We've also learned how gravity shapes the universe through its influence on a large range, and how relativity reveals how extraordinary gravity is, and that time travel into the future is technically possible. Dr. Kurichi's work has shown us that the fabric of the stage, space-time, might itself be made of these small mathematical connections known as loops, and that a possible theory for gravity and a theory for everything is possible, but not complete yet. We've covered a lot, but if there's something I want you all to leave tonight with, it's this. It's true that we were born too early to explore the universe, but that doesn't stop us from exploring our place in the universe through science. Stay curious, everyone. Thank you all, and have a good night. We will stay here to answer any questions for a little bit, but that is going to conclude tonight. Thank you all. Here's some references if anyone was curious.
Yeah, thank you so much, William. That was a wonderful talk. Really great way to kick off our multiculturalism at the Observatory program. Just for everyone watching, next week at the same time, Wednesday at 8:30, William will be giving this talk again, but this time completely in Spanish. So if you're interested in joining again or have any friends who'd like to join, next week we're going to be doing the Spanish version of this talk.
We will see you then.
And we'll stick around for just a couple more minutes to see if there's any questions in the chat. But otherwise, thank you very much for joining us. It's too dark to see the telescope.
Yeah.
Otherwise, people could see it. It's kind of cool when it moves around. But
I mean, we're barely visible too.
yeah, we could be anywhere. Who knows what we're actually at the observatory.
We have a question.
Okay, so Raymond's asking, is there any way that dark energy plays into any of this?
Well, as we were talking about earlier, dark matter is very important into the study of gravity, but with dark energy, that really ties into the whole cosmology aspect of it and how we're moving away from a big crunch.
More of just like accelerating, or the universe is expanding at accelerating rate. I remember vaguely reading about an article where dark energy might be like a way for us to maybe potentially find the graviton. Don't quote me on that, but dark energy can play into like learning more about gravity. And the graviton, by the way, is the force carrier for gravity. All the other fundamental forces have not graviton, but they have a force particle. And we actually have evidence for them, but we don't have evidence for gravity's force particle, which is the graviton.
Yeah, and I would just add that like dark energy is a really big player, like you were saying, in the cosmology aspect. Like if we think about the energy budget of the universe, like what is it that's contributing in total the energy of the universe? Like dark energy, we think is like upwards of 70% of the energy in the universe, and we think it's the thing behind the fact that our universe is expanding in the first place. So it's kind of like it has similarities to gravity in that like we can kind of see its effect. We can see our universe expanding, but we have these fundamental questions about like what even is it? Like, so there's a whole there's a whole host of people around the world who are working on that question too, which is what the heck is dark energy? Why is it so dominant, and why is it so hard for us to interact with? Like, kind of a secret of astronomy is whenever something is named dark blank, it means we have no idea what it is. So dark matter, we have no idea what it is. Dark energy, we have no idea what it is. Hopefully there won't be any more dark things, because then we won't know what those are either. But yeah, I think it has like a huge role to play in kind of the evolution of our universe, yet it's like seriously we just don't know that much about it, which is crazy.
Thank you for the question, by the way. Excellent question.
Well, we're approaching the kind of hour, so we probably should wrap it up. We've been having so much fun over here. But yeah, thank you all again for joining. It has been wonderful, and thank you very much to William for the great talk. And catch us here next week if you'd like to do it again in Spanish.
Thank you all for coming tonight.
Great. Bye.